Okay, so let's move over to decoding our blocks. So ignoring the encryption, if we get a single large integer back, how do we separate it back up into the characters? It's kind of magic, right? So what we do is we have to reverse the operations that we did before. And so this is a idempotent operation both ways, which means that everything that we did before, we can undo. And so before we started out with 0, and then we increasingly, based upon the index of a letter in the alphabet that we have, and the length of that alphabet, and its position in the word, we did multiplication and raised it to a power. So until we built up the whole thing. Now we have to start with a number and pull off the last letter, and then the next one, and then the next one, the next one, until we're done. So this is actually remarkably similar to the transposition cipher from yesterday. So after we go through this, maybe take some time in your brain, if you're interested, to think about how this is really a very similar process, just a little bit more complicated. So the first thing that we do is that we divide the integer that we have by 66, and this is by the block length, minus 1, and we round down. And for that, you'll get the first index to the last character. And then you mod that same integer by 66 to the power of message length, block length, minus 1, and that gives you the next block integer ready to go. And so every time, first you do integer division to get the character index, and then you do integer modulus to get the next block number, integer division to get the next character number, integer modulus to get the next block number, all the way until the block size is down to 0. And so if we have a giant number that we made from 169 different characters, we're going to need to do division and modulus once each for each character. So this is a process that models itself to recursion very well. And the only tricky bit is that the same way with transposition cipher, how we had to deal with the fact that the message length is not always going to be exactly a multiple of the block length. So if the message has 54 characters in it, and we do this division 60 times, we're going to do it 6 times too many, which means that we're going to get some garbage, potentially a divide by 0 error, or some kind of decryption that doesn't make any sense at all. And so what we've got to do first is we've got to determine if there's any extra characters that at the end, that we're going to need to ignore. And so I did that very much the same way as we handled the transposition cipher, of just thinking about this as like a matrix. And so if we get the area of all of the full blocks, and then we minus the length of the message, we'll end up with how many positions in block size fewer are needed for the final computation. Then, if we have 0 missing characters, we're fine. That means that the same block size can be used for the last block as every single other block. Otherwise, we want to actually mod the block size of the other ones by the missing characters to get the number of computations that we need to achieve. So here, then we just simply build up our structure. Then, since we're starting from the end and working our way back, we've got to reverse it. And then we've still got a list of chunks. So we flatten it, and then we're good to go.
How do you get the message length if you only have a list of checks?
We have to encode the message length with the message.
Okay, so the encrypted message will be the list of integers and the message length?
What we'll do is we will directly write the integer message length and then the encryption. And so the encryption will not be in a list form. That would actually introduce quite a bit of vulnerability. So we'll tell the attacker what the message length was, and we know we'll tell, yeah, so the attacker will know what the message length was, what the block size was, and what the decrypted text is, or the encrypted text. The attacker will know everything. What are we doing? No, but they'll know the block size, the message length, and the encrypted message. Those things they'll know, but it still won't be enough for them to break it. So if all we were doing was this, the encoding and the decoding, this would not work. But there's a step in the middle of encryption that I've left out because the decoding and the encoding are very similar. And the reason why the decoding and the encoding is important is because that prevents the encryption from having the ability to be vulnerable to letter frequency analysis. And also, I think we can do this. We should be able to just concat map reverse, right? I won't mess with that right now. Yeah, so this is where the recursion happens. So this case right here, this is the last block side. This is the last block. And we just right now wrap that up in its own list and then concatenate that to the result of this one. And this is recursive in that decode block itself here, this is where the actual work of the math is being done. So if we ever get to -1, then we return the empty list. Otherwise, we call decode block with block size and block. We then do the math here. So the divisor is map.size of our symbol map to the power of block size. The character index is calculated using the integer division operator. The next block is calculated using the integer modulus operator. We look up the character in the map, and then we pattern match on just or nothing. If we find it, we cons it on to a recursive call to decode block with block size -1. So if we know that we started out with 4 characters, the first time we find the character using integer division and modulo, and we get the character, and then we call our function again now with 3. And then we run the integer division and modulo with the 3 as a block size, so 66 to the 3rd in the divisor, and we get a character, and we cons that onto the result of our function running with 2, which gives us a character which we call with 1, which finally we call with 0 to get the 0th index. And then finally, we call with -1, which cons each cell of the list onto the empty list. So just classic list recursion here. And that's decoding and encoding. Any questions I can answer here for the decoding and the encoding? And the difference here is that even though this one in the last cell recurses itself, it's only called directly on a single block, the last of the blocks. And then this decode is mapped over each of init blocks, which returns everything except for the last block. And there's definitely quite a bit of performance that could be done here. Both init and last with singly linked lists are quite slow when the lists are very long because they have to traverse the entire list. So definitely some performance stuff that we could improve here, similar to the techniques that we had to work on with the other ciphers. Okay, so let's take a look finally at the encryption. So once we have our number, it's actually quite straightforward. So we have C being equal to M to the power of E mod N to encrypt, and M being equal to C to the power of D mod N to decrypt. So whoops. So when we encrypt the message, we take in the message, the key, and the block size. And we pull out the N and E values from the public key. Then we call encode blocks on the message with the block size, and that gives us the blocks. And then we're going to map an anonymous function using the map operator over each of the blocks. And this one is going to call power mod, which is our very, very fast operation, which is going to say to integer of block to the power of E modulus N. And that is going to give us the encryption. When we decrypt, we simply do it in reverse. So we take the encrypted blocks, the message length, the key, and the block size, and we pull N and D out of the private key, and then we get the blocks by mapping over the encrypted blocks with power mod again, and this time we use from integral block with D and N. And then we have now a list of each decrypted block. And from here, all we have to do is call decode blocks on the blocks with the block size and the message length. And really, that's the whole shebang. That's a textbook RSA in ye old Haskell. So when it comes to the question of why this is secure, there's a few reasons why why this can't be hacked. And so there are basically an infinite amount of keys to check. So we can't just brute force it, because all we know is that in order to generate the keys, a random prime number between 2 to the 1024 minus 1 and 2 to the 1024 was created. And so we need, in order to brute force it, we would need to try all combinations of prime numbers between that range, which is just not feasible for most, for really all computers, unless the NSA has some fancy quantum ones that we don't know about. And we can't use the dictionary attack like was done with the transposition cipher, because there's no way to get a frequency analysis on letters, because we are not doing any kind of letter-to-letter conversion or word-to-word conversion. We're just doing letters down to blocks of large integers that, in turn, the integers are encrypted. So that's not going to work. The word pattern can't work because every word will be encrypted differently, because the position in both the letter in each block as well as the fixed position of the key in the map are required to do the encryption. So each word is going to be encrypted differently every single place in the message. And then finally, the frequency analysis of any kind can't work because there's no way to get a frequency count of the individual characters. And the other important thing is to know that even though we know the key sizes from the public file, and the cryptanalyst knows the range that the prime numbers are in, that there's really just no way beyond trying to brute force the factorization of the primes, which is something that, as of yet, we don't have a mathematical proven way of doing, which means that brute force all the way, which means that you're just totally reliant on how fast computers are. And right now, there's no known technology that can brute force these fast enough. So essentially, that's what I have for you as far as the RSA stuff goes. We could now, for the remainder of our time, go back to some of the stuff that we didn't get to go over yesterday, or we could talk about how Morse code works and some data structures that work around Morse code. Does anybody have preference? Okay. So So how many of you had a pretty clear idea of how RSA worked, or how to do kind of a naive implementation? Was there anybody that, okay. Yeah, okay, good. I was kind of worried. It's like, you never know, but.
I knew the number theorem
Yeah, the blocks I totally didn't know at all. I knew that there was something about, I knew that the public and private keys came from big prime numbers, and prime factorization is like the way that they're secure, and that you encrypt with the public key and you decrypt with the private key. But the nitty-gritty of how it worked, I had no clue. And I was surprised even just how difficult it is just to simply test for a number to be prime. Like, you just really can't have to have some pretty cool stuff. Let me find my Morse code notes real quick, and then we'll jump into that. Okay. This should get us into actually some of the talk of data structures in Haskell and traversing stuff. So that would be nice too, because we haven't had a ton of that. But so this is kind of the extra credit section. But so I talked a little bit about this yesterday, but for codes and ciphers, really a cipher is a special type of code where it's meant to be totally not understandable. And a code is meant to be understandable. So it's meant to have an internal logic and structure that aids in like condensing or transporting data in such a way that you can wrap it out. And so one thing that I had no idea, like I always knew Morse code is dots and dashes, right? But actually it's a tree structure. So each spine of the tree is a function, and the function is either a dot or a dash. And each node has two spines, a dot and a dash. So when we start, a single dot is an E, and then a single dash is a T. Two dashes is an M. Two dashes and then a dot is a G, and so on. So if you pick anything on any character on this chart, you can simply traverse back to home to figure out what the encoding is. So H would be dot, 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 dot. R would be dot, dash, dot. P would be dot, dash, dash, dot. And so this wasn't just somebody who took 26 or 50 or whatever unique pictorial values and mapped it to a letter, but there's actually a very strong and sound mathematical structure to it. And I actually learned while I was doing this that there was a great, so in the late 40s, there was a man in the United States named James Pride, and he was a black man, and he tried out to become a pilot for the Air Force, and he passed with flying colors, but because of racist policies, he was denied position as a pilot, even though they were supposed to let him in. And he was stuck kind of in this limbo state. And at the same time, somebody, nobody knows exactly who, but people think it was Eleanor Roosevelt, who was the first lady for Franklin Delano Roosevelt, mandated that in the United States intelligence services, there needed to be a certain amount of diversity. And because of that, he got the opportunity to work for what was one of the intelligence services that now evolved into some combination of the NSA or the CIA. And but the government officials that were implementing this program were very cranky and pretty backwards and pretty awful, actually. And so they were hiring people who were incredibly talented, like this man, James Pride, and they stuffed them all just in the basement somewhere. And they just barely gave them equipment to do anything and had them working all day. But there were a lot of really phenomenally intelligent people in this all-black like code cracking thing. And this guy, James Pride, was so good that he could just take a look at Morse code tape written in codes, even encrypted Morse code, and just read it out as if it was just prose. And so this is just kind of going on for a while, for a couple years, where there's this like somehow crack team of people that nobody knows exists. And they have a single boss who's a white man, but the white guy is so frustrated about having to be the boss of the black team that he actually never even visits. So he has no idea what's going on. And the person who ends up managing the group ends up being another black man who's totally like a master's level educated guy, but who, for other reasons, because of also of segregation and racism, happened to be working as janitor of the basement. And so you have like all these incredibly overqualified people just like sitting doing great work. And then one day, one of the higher ups is like, what is going on with this like crack squad of people? And he thinks that they must be like cheating on their numbers because they're being so productive. And when he goes down there, he sees, among other things, this guy, James Pride, who's just like reading, and like his brain is just like taking this tree structure, and just like filtering it out. And he's like, oh my gosh, like what's going on? Like, and so they ended up promoting him to a level of importance, along with a bunch of other people. And it wasn't until the late 1990s that anybody even knew that any of this happened, because it was all, the whole story was confidential, privileged information, because it's all spy agencies, they lock down everything. But I thought that was a pretty amazing story about just some people have some very, very beautiful minds. Okay, so we know that that Morse code is a mapping of really characters or strings to codes, right? So one thing that we could do is we could say that we could make ourselves a new type, a Morse code type, and give it a string. And then we could just say, let's make a dictionary. The dictionary is going to be a list of Morse code and character. And then we could say something like this, right? And so on, right? And then if we wanted to, we could even use one of the, like we could use map.fromList to make this an efficient lookup between keys and values. And we could even flip it and what have you. But since we know that this is actually a tree structure, we can do something even cleverer. So we can make ourselves a new structure, which is going to be a tree of characters. And so then the tree, sorry. Our tree can be a leaf, which means that we've terminated, we've got to the end here, or it can be a branch. And for the branch, we're going to give it a tag of type A, and a left, which is going to be a tree of A, okay, and so now that we've got our data type, so if we want to create a new instance of something, like let's say we want to create the start. So what we can do is we can say branch, and we can give it the empty character, and then branch E, and let's just put a leaf here. So now we've got this idea where our start is the empty character, and then if we go left, we land on E, and if we go right, we land on T. So now we've encapsulated the idea that the dots are always going to be associated with the lefts in every situation, and the rights are always going to be associated with the dashes. So then we can do something super cool. So once we've got that whole thing built up, we can write a function decode letter, and since each of these are going to be functions, we can actually concatenate tag, or excuse me, compose tag with fold L, and then we can flip step inside of our dictionary, assuming this was written out all the way. You've got that. Oh, yeah. Where step this equals left, and step So let's take a second and think about this. So flip takes a function, a binary function, and flips its arguments. So flip takes any A to B to C and returns a B to A to C. And so the cool thing about this is, so it takes a function itself, A to B to C, and then returns B to A to C. And it can be kind of hard to see what's going on here, but if you add another parentheses here, I think it helps a lot. Because now you can see that it takes a single function and it returns a single function where the arguments are reversed. And you don't need the parentheses here because of currying. So if you only apply a function, then what you get back is just B to A to C, which is a function. So let's see. Let's make sure that we can get this compiling. Let's see what I got. So I haven't implemented foldable for our custom tree type. Which I believe is the issue that we've got. Yeah. And we haven't implemented traversable on the tree itself.
Can it derive it?
With the fancy GHC extension, we can. I believe we can do deriving via. out of the box, you can only derive EQ, ORD, and show, and enum, I think, are the 4 that you can do. But let's try this. Cross our fingers. Hey. Let's see if that works. A possible fix, using a type annotation to specify what T0 should be. Let's see if we can muscle our way through this. We're also about out of time.
I said that we will need another 10 minutes, so we can stay here.
Okay.
At 5:30.
Okay, well, we'll see if we can get to a good spot with this, and if not, we'll forgive ourselves. So let's try this. So
the error message from the compiler doesn't make sense to me. It proposes a faultable instance for either.
So I think what it's saying is where fold L is going, there's multiple folds that it could do. Maybe, and it's not sure if we're trying to use the fold from an either instance or from the tree instance or from something else. So I was trying to tell it, hey, specifically here, I was trying to tell it exactly what the instance was, but I didn't quite get there. Well, I'll hack on this, and if I get into a good spot, I'll post it in the channel. But thank you all so much for your attention and for coming to class.